Picture this. Every single day, somewhere around the world, massive factories process over 500,000 tons of sugar. That's enough sweetness to fill nearly 25,000 trucks, rolling off production lines in an endless stream of crystalline perfection. From the morning coffee that jumpstarts your day to the birthday cake celebrating life's sweetest moments, sugar touches virtually every aspect of human existence. Yet behind this ubiquitous commodity lies one of agriculture's most fascinating industrial transformations, a process so intricate and massive in scale that it represents nothing short of modern agricultural engineering at its finest. The global sugar industry generates over 180 million tons annually, worth more than $50 billion worldwide. This isn't just about satisfying our collective sweet tooth. Sugar serves as a fundamental ingredient in food processing, pharmaceuticals, and even biofuel production. The journey from field to factory represents centuries of agricultural innovation, where traditional farming wisdom meets cutting-edge industrial technology. But have you ever wondered how those tiny sugar crystals that dissolve so effortlessly in your cup actually come to be? The answer lies in a remarkable process that transforms humble plant matter into one of the world's most essential commodities. The modern sugar industry stands as a testament to human ingenuity in agricultural processing. What began as a luxury item reserved for the wealthy has evolved into a global necessity, with sugar production facilities operating on every continent except Antarctica. These aren't just factories, they're agricultural cathedrals where science, engineering, and farming expertise converge to create something extraordinary. The scale alone is breathtaking. A single modern sugar processing facility can handle up to 15,000 tons of raw material daily, operating around the clock during harvest season to capture every precious moment of peak sugar content. Today's sugar production represents a perfect marriage between agricultural tradition and industrial innovation. Modern facilities employ everything from satellite-guided harvesting equipment to computer-controlled crystallization chambers, yet the fundamental process remains rooted in principles discovered centuries ago. The industry supports millions of farmers worldwide. From small family operations to massive commercial enterprises, all united by the shared goal of transforming sunlight and soil into pure sweetness. This transformation doesn't happen by accident. It requires precise timing, sophisticated equipment, and an understanding of both agricultural science and industrial engineering that continues to evolve with each passing season. The sugar industry today encompasses two primary source crops: sugarcane and sugar beets, each requiring entirely different agricultural approaches, yet ultimately yielding the same crystalline result. Sugarcane dominates tropical and subtropical regions, thriving in countries like Brazil, India, China, and Thailand, where year-round growing seasons allow for continuous production cycles. These towering grasses can reach heights of 20 feet or more, their thick stalks packed with sucrose-rich juice that forms the foundation of most global sugar production. Meanwhile, sugar beets flourish in temperate climates across Europe, North America, and parts of Asia, storing their sweetness in bulbous roots that can weigh several pounds each. The economic impact of sugar production extends far beyond the processing facilities themselves. In Brazil alone, the sugar industry employs over 1.2 million people directly, with millions more depending on related industries from equipment manufacturing to transportation. The United States processes approximately 8 million tons of sugar annually, supporting rural communities across more than 20 states. European sugar production, while smaller in global terms, represents a crucial component of agricultural policy and rural development, with countries like Germany, France, and Poland maintaining sophisticated sugar beet operations that rival any industrial process for precision and efficiency. Modern sugar production has revolutionized traditional farming practices through technological innovation. GPS-guided tractors now plant sugarcane with millimeter precision, while drone technology monitors crop health across thousands of acres. Satellite imagery helps predict optimal harvest timing, ensuring that sugar content reaches peak levels before processing begins. These advances haven't eliminated the need for agricultural expertise. Instead, they've amplified it, allowing farmers to make more informed decisions based on real-time data about soil conditions, weather patterns, and crop development. The shift from traditional to modern sugar production methods represents one of agriculture's most dramatic transformations. Historical sugar production relied heavily on manual labor, with workers using machetes to cut cane by hand and simple mills to extract juice. Today's operations employ massive harvesters that can process 500 tons of sugar cane per hour, while computer-controlled systems monitor every aspect of production from field to final packaging. This evolution hasn't just improved efficiency, it's also enhanced safety, reduced environmental impact, and created new opportunities for agricultural innovation. The foundation of all sugar production begins with understanding the biological processes that create and store sucrose in plants. Sugarcane accumulates sucrose in its stalks as a natural energy reserve, with concentrations reaching 15 to 20% of the plant's total weight under optimal conditions. This sucrose formation responds to specific environmental triggers, including temperature variations, sunlight exposure, and soil moisture levels. Modern agricultural science has identified the precise conditions that maximize sucrose production, leading to cultivation techniques that can increase sugar yields by 30% or more compared to traditional methods. Sugarcane cultivation starts with careful selection of seed material, typically using stem cuttings from the previous year's crop. These cuttings, called sets, contain multiple nodes that will sprout into new plants under proper conditions. The planting process requires precise timing. Too early, and frost damage can destroy emerging shoots. Too late, and the growing season becomes insufficient for maximum sugar development. Modern plantations use GPS-guided equipment to ensure uniform spacing and optimal row alignment, creating conditions that maximize both sunlight exposure and mechanical harvesting efficiency. The growing cycle for sugarcane spans 12 to 18 months, depending on climate and variety. During this period, the plants undergo several distinct growth phases, each requiring specific agricultural management. The initial establishment phase focuses on root development and shoot emergence, requiring careful moisture management and protection from pests. The grand growth phase sees rapid vertical development, with plants adding several inches of height daily under optimal conditions. The maturation phase is when sucrose accumulation reaches its peak, requiring precise monitoring to determine optimal harvest timing. Soil preparation for sugarcane cultivation represents a sophisticated balance of chemistry and physics. The ideal soil provides excellent drainage while retaining sufficient moisture, maintains proper pH levels between 6.0 and 7.5, and contains adequate organic matter to support healthy microbial activity. Modern sugar operations invest heavily in soil testing and amendment, often applying customized fertilizer blends based on detailed soil analyses. This scientific approach to soil management can increase yields by 25% or more, while reducing environmental impact through precise nutrient application. Water management in sugarcane cultivation requires careful balance throughout the growing season. Young plants need consistent moisture to establish root systems, while mature plants benefit from controlled water stress that concentrates sucrose in the stalks. Modern irrigation systems employ sensors and weather data to optimize water application, reducing consumption by up to 40% compared to traditional methods. This precision irrigation not only conserves water resources but also improves sugar quality by preventing dilution of sucrose concentrations. The harvesting phase represents the culmination of months of careful agricultural management. Sugarcane harvesting requires precise timing. Too early, and sucrose concentrations remain below optimal levels. Too late, and natural conversion processes begin reducing sugar content. Modern harvesting operations use sophisticated equipment that can cut, clean, and load sugarcane at rates exceeding 100 tons per hour. These machines employ sharp rotating blades to cut stalks at ground level, powerful fans to remove leaves and debris, and conveyor systems to load cleaned cane directly into transport vehicles. Transportation from field to factory represents a critical phase where time becomes the enemy of quality. Once cut, sugarcane begins losing sucrose content through natural respiration and enzymatic processes. Modern operations have developed sophisticated logistics systems that minimize the time between harvest and processing, often delivering cane to factories within 24 hours of cutting. This rapid turnaround requires careful coordination between harvesting crews, transportation fleets, and processing facilities, all working together to preserve maximum sugar content. The initial processing phase begins the moment sugar cane arrives at the factory. Massive conveyor systems transport the raw material through a series of preparation steps designed to optimize juice extraction. The cane first passes through chopping machines that reduce long stalks into uniform pieces, creating optimal conditions for subsequent processing. These chopped pieces then move through shredders that break down the fibrous structure, exposing the sugar-rich interior to extraction equipment. Juice extraction represents the heart of sugar processing, where mechanical engineering meets agricultural science. Modern extraction systems employ a series of heavy-duty mills that crush the prepared cane between massive steel rollers. These mills operate under tremendous pressure, often exceeding 1,000 tons per square inch to squeeze every drop of juice from the fibrous material. The extraction process typically involves 4 to 6 mill stands, each designed to extract additional juice while preparing the fiber for efficient processing. The extracted juice contains much more than just sugar. It's a complex mixture of sucrose, water, minerals, organic compounds, and suspended solids. This raw juice typically contains 12 to 15% sucrose, along with various impurities that must be removed through sophisticated purification processes. The juice's quality depends heavily on the agricultural practices used during cultivation, the timing of harvest, and the speed of processing after cutting. Modern facilities can process over 10,000 tons of sugarcane daily, extracting more than 1.5 million gallons of raw juice that will undergo extensive purification. The purification process begins with clarification, where lime and heat work together to remove impurities and suspended solids. The raw juice is heated to approximately 100 degrees Celsius, while carefully measured amounts of lime are added to neutralize acids and precipitate unwanted compounds. This process, known as defecation, causes impurities to form flocks that can be separated from the clean juice. The clarified juice emerges as a clear, golden liquid containing approximately 15% sucrose, still far from the concentrated sweetness of final sugar products. Following clarification, the juice undergoes evaporation to concentrate the sucrose content. This process employs multiple effect evaporators that use steam to remove water while minimizing energy consumption. The evaporation process typically reduces the juice volume by 80% or more, creating a thick syrup containing 60 to 65% sucrose. This concentration process requires precise temperature and pressure control to prevent sucrose degradation while maximizing water removal efficiency. The concentrated syrup then enters crystallization chambers where the magic of sugar formation truly begins. This process requires exquisite control of temperature, concentration, and agitation to encourage sucrose molecules to form perfect crystals. The crystallization process typically begins with the introduction of seed crystals, tiny sugar particles that provide nucleation sites for crystal growth. Under carefully controlled conditions, these seeds grow into larger crystals as additional sucrose molecules attach to their surfaces. The crystallization process unfolds in multiple stages, each designed to extract maximum sugar yield while maintaining crystal quality. The first crystallization produces what's known as A sugar, the highest grade product with the largest crystals and purest composition. The remaining mother liquor, still containing significant sucrose, undergoes additional crystallization stages to extract B sugar and C sugar, each with progressively smaller crystals and higher impurity levels. This multi-stage approach ensures that virtually all recoverable sugar is extracted from the original cane juice. Centrifugal separation follows crystallization, where massive centrifuges spin the crystal syrup mixture at high speeds to separate solid sugar crystals from liquid molasses. These industrial centrifuges can process several tons of material per hour, using centrifugal force thousands of times stronger than gravity to achieve complete separation. The separated crystals emerge as raw sugar, still containing some surface molasses that gives them their characteristic golden color and distinctive flavor. The final refining process transforms raw sugar into the pure white crystals familiar to consumers worldwide. This process begins with affination, where the raw sugar is mixed with concentrated sugar syrup to dissolve surface molasses while leaving the crystal structure intact. The affined sugar then undergoes carbonation, where carbon dioxide and lime work together to remove remaining impurities and create pure white crystals. The carbonation process requires precise control of temperature, pH, and chemical additions to achieve optimal results. Quality control throughout the sugar production process employs sophisticated analytical equipment and rigorous testing protocols. Modern facilities test sugar samples hundreds of times daily, measuring everything from sucrose content and moisture levels to color and crystal size distribution. These quality control measures ensure that every batch of sugar meets strict industry standards for purity, consistency, and performance. Advanced laboratories use techniques like high-performance liquid chromatography and near-infrared spectroscopy to analyze sugar composition with remarkable precision. Packaging and storage represent the final stages of sugar production, where engineering precision meets consumer convenience. Modern packaging systems can fill and seal thousands of bags per hour, using automated equipment that ensures consistent weights and proper sealing. The packaging process employs multiple quality checks, including weight verification, seal integrity testing, and visual inspection to ensure that every package meets quality standards. Large-scale operations often include automated palletizing systems that stack finished products for efficient shipping and storage. The transformation of sugarcane into pure sugar crystals represents one of agriculture's most remarkable achievements, combining traditional farming wisdom with cutting-edge industrial technology. From the sun-drenched fields where sugarcane grows to the sophisticated factories where crystallization occurs, every step in the process reflects centuries of agricultural innovation and human ingenuity. This massive industry continues to evolve, driven by the constant pursuit of efficiency, quality, and sustainability that defines modern agriculture. The journey we've just witnessed from growing fields to crystalline perfection represents just one facet of agriculture's incredible capacity for transformation. The same principles of precision, scale, and innovation that drive sugar production appear throughout modern farming, creating the abundance that feeds our world. As we move forward, we'll discover how these same agricultural principles apply to other essential crops, each with its own unique challenges and remarkable solutions. The same agricultural precision that transforms sugarcane into crystalline sweetness has revolutionized another crop that most people never think about, yet encounter dozens of times every day. Hidden within the foods we eat, the products we use, and even the fuel that powers our vehicles lies a remarkable little bean that has quietly become one of the world's most valuable agricultural commodities. We're talking about soybeans, those humble, oval-shaped legumes that have transformed from an ancient Asian crop into a global protein powerhouse worth over $140 billion annually. Every year, farmers worldwide harvest more than 350 million tons of soybeans, enough to fill a train stretching from New York to Los Angeles and back again twice. This isn't just impressive, it's revolutionary. Soybeans contain approximately 40% protein, making them one of nature's most efficient protein factories. While most people associate protein with meat and dairy, soybeans quietly provide the protein foundation for countless products, from the soy milk in your morning latte to the protein isolates in energy bars, from the lecithin that keeps chocolate smooth to the biodiesel that powers city buses. The story of soybeans represents one of agriculture's most remarkable success stories, where ancient wisdom meets modern innovation to create something extraordinary. Originally cultivated in China over 5,000 years ago, soybeans were considered one of the 5 sacred grains, essential to Chinese civilization. Today, this ancient crop drives modern agriculture across 6 continents, supporting millions of farmers and feeding billions of people through direct consumption and as livestock feed. The transformation of soybeans from a regional Asian crop to a global agricultural superstar demonstrates how agricultural innovation can reshape entire food systems. What makes soybeans truly fascinating is their unique ability to fix nitrogen from the atmosphere, essentially fertilizing themselves while growing. This remarkable biological process, facilitated by symbiotic bacteria called rhizobia, allows soybeans to convert atmospheric nitrogen into plant-available forms, reducing the need for synthetic fertilizers. A single soybean plant can fix up to 300 pounds of nitrogen per acre, making soybeans not just a protein source but also a natural soil enhancer. This dual benefit has made soybeans a cornerstone of sustainable agriculture, improving soil health while producing valuable crops. The global soybean industry today spans every continent except Antarctica, with production concentrated in 4 major regions that together account for nearly 90% of world output. The United States leads global production, with states like Iowa, Illinois, and Minnesota producing over 120 million tons annually. Brazil follows closely, with vast soybean plantations stretching across the Cerrado savanna, where innovative farming techniques have transformed previously marginal lands into highly productive agricultural regions. Argentina rounds out the top 3 producers, with sophisticated operations that have made soybeans the country's most valuable export commodity. Modern soybean production represents a perfect synthesis of traditional farming knowledge and cutting-edge agricultural technology. Today's soybean farmers employ precision agriculture techniques that would have seemed like science fiction just decades ago. GPS-guided tractors plant soybeans with centimeter-level accuracy, while variable rate technology adjusts seed spacing and fertilizer application based on detailed soil analyses. Drone surveillance monitors crop health across thousands of acres, identifying pest problems and nutrient deficiencies before they become visible to the human eye. These technological advances have increased average soybean yields by more than 50% over the past 3 decades, while reducing environmental impact through precise resource management. The economic significance of soybean production extends far beyond farm gates. The global soybean trade generates over $60 billion annually in export revenues, making it one of the world's most valuable agricultural commodities. In the United States alone, soybean exports support over 280,000 jobs, from farmers and processors to transportation workers and port employees. The soybean industry has become so integral to global agriculture that commodity exchanges in Chicago, Sao Paulo, and other major cities track soybean prices minute by minute, with fluctuations affecting everything from livestock feed costs to biodiesel production. The transformation of soybeans from seed to final products begins with understanding the plant's unique biology and growth requirements. Soybeans thrive in temperate climates with warm summers and adequate rainfall, requiring approximately 120 to 150 frost-free days to reach maturity. The plants prefer well-drained soils with pH levels between 6.0 and 7.0, though modern varieties have been developed to tolerate a broader range of conditions. This adaptability has allowed soybean cultivation to expand into previously unsuitable regions, from the Amazon basin to the Canadian prairies. Soybean breeding represents one of modern agriculture's most sophisticated achievements, combining traditional plant breeding with advanced genetic techniques. Today's soybean varieties result from decades of careful selection and crossbreeding, creating plants that produce higher yields, resist diseases, and tolerate herbicides. Some modern varieties can yield over 70 bushels per acre under optimal conditions, compared to traditional varieties that rarely exceeded 25 bushels per acre. This yield improvement hasn't come at the expense of protein content. Modern soybeans maintain the high protein concentrations that make them so valuable, while dramatically increasing total protein production per acre. The planting process for soybeans requires precise timing and sophisticated equipment to ensure optimal results. Modern planters can place individual seeds at predetermined depths and spacing, creating uniform plant populations that maximize yield potential. The planting process typically begins in late spring, when soil temperatures reach 55 to 60 degrees Fahrenheit and moisture conditions are optimal for germination. Farmers use soil thermometers and moisture sensors to determine exact planting timing, understanding that rushing the process can result in poor germination and reduced yields. Seed treatment represents a crucial aspect of modern soybean production, where advanced chemistry protects vulnerable seeds during the critical germination period. Seeds are coated with fungicides to prevent soil-borne diseases, insecticides to protect against early-season pests, and inoculants containing beneficial bacteria that enhance nitrogen fixation. This seed treatment process requires specialized equipment and precise application rates to ensure effectiveness without damaging the seed or surrounding environment. The treated seeds emerge as healthy plants with enhanced resistance to early-season stresses. The early growth stages of soybeans require careful management to establish strong, healthy plants capable of maximum production. During the first few weeks after planting, soybeans are particularly vulnerable to weeds, diseases, and insect pests. Modern farmers employ integrated pest management strategies that combine cultural practices, biological controls, and targeted chemical applications to protect young plants. This holistic approach minimizes environmental impact while ensuring healthy crop establishment. Nitrogen fixation in soybeans represents one of nature's most remarkable agricultural processes, where atmospheric nitrogen is converted into plant-available forms through a sophisticated biological partnership. Rhizobia bacteria form nodules on soybean roots, creating specialized environments where nitrogen fixation occurs. This process requires specific soil conditions and bacterial strains, leading to the development of specialized inoculants that ensure optimal nitrogen fixation. The result is a crop that can meet most of its nitrogen needs without synthetic fertilizers, reducing both production costs and environmental impact. The flowering and pod development stages of soybeans represent critical periods that determine final yield potential. Soybeans typically begin flowering 45 to 60 Daltonses after planting, depending on variety and growing conditions. The plants produce small, white or purple flowers that self-pollinate and develop into pods containing 2 to 4 seeds each. This reproductive phase requires adequate moisture and nutrients, making it a focus of intensive management. Modern farmers monitor flowering progress closely, adjusting irrigation and fertilization to optimize pod development. Water management during soybean production requires sophisticated understanding of plant needs throughout the growing season. Young soybeans need consistent moisture for establishment, while mature plants can tolerate some drought stress. The critical period for water availability occurs during flowering and pod filling, when water stress can significantly reduce yields. Modern irrigation systems employ soil moisture sensors and weather data to optimize water application, ensuring adequate moisture during critical periods while avoiding overwatering that can promote disease development. Pest management in soybeans involves dealing with a complex array of insects, diseases, and weeds that can significantly impact yields. Common insect pests include aphids, bean leaf beetles, and corn earworms, each requiring different management strategies. Disease pressures vary by region and season, with problems like sudden death syndrome and white mold causing significant yield losses under favorable conditions. Modern farmers use integrated pest management approaches that combine resistant varieties, cultural practices, and targeted treatments to manage these challenges effectively. The maturation process of soybeans involves a gradual transition from green, moisture-filled pods to dry, harvestable beans. This process typically takes 100 to 150 Daltons wise from planting, depending on variety and growing conditions. As soybeans mature, the plants begin to yellow and lose their leaves, while the pods turn brown and the beans inside reach their final size and composition. Farmers monitor moisture content closely during this period, preparing for harvest when moisture levels drop to 13 to 15%, the optimal range for safe storage. Harvesting soybeans requires sophisticated equipment and precise timing to maximize yield and quality. Modern combine harvesters can process 15 to 20 acres per hour, using cutting platforms specifically designed for soybeans. The harvesting process involves cutting the plants, separating the beans from the pods, and cleaning the grain to remove chaff and debris. This mechanical harvesting requires careful adjustment of combine settings to minimize grain loss while maintaining quality standards. The harvested soybeans undergo immediate quality assessment to determine their suitability for different end uses. Factors like protein content, oil content, moisture level, and foreign material percentage all influence market value and processing options. High-protein soybeans command premium prices for food applications, while high-oil varieties are preferred for processing into soybean oil. This quality differentiation has led to the development of specialized varieties tailored for specific market segments. Transportation from farm to processing facilities represents a critical phase where logistics expertise meets agricultural production. Soybeans are typically stored in on-farm bins or local elevators before being transported to processing facilities or export terminals. The transportation network includes trucks, rail cars, and river barges, all working together to move soybeans efficiently from production areas to processing centers. This transportation system handles over 4 billion bushels of soybeans annually in the United States alone, requiring sophisticated coordination and infrastructure. The processing of soybeans into various products represents one of agriculture's most versatile and valuable transformations. The primary processing step involves crushing soybeans to separate oil from meal, typically yielding about 18% oil and 80% meal from each bushel. This crushing process employs massive machinery that can process thousands of bushels per hour, using mechanical pressing or solvent extraction to maximize oil recovery. The resulting soybean oil serves as cooking oil, industrial lubricants, and biodiesel feedstock, while soybean meal becomes high-protein livestock feed. Soybean oil processing involves multiple refining steps that transform crude oil into finished products suitable for various applications. The refining process removes impurities, neutralizes acids, and eliminates unwanted flavors and colors. Modern refining facilities can process millions of gallons of soybean oil annually, creating products ranging from cooking oil and margarine to industrial lubricants and biodiesel. The versatility of soybean oil has made it one of the world's most consumed vegetable oils, with applications extending far beyond food production. Soybean meal processing focuses on maximizing protein content and digestibility for livestock feed applications. The meal undergoes heat treatment to deactivate anti-nutritional factors and improve protein quality. Modern processing facilities can produce various grades of soybean meal, each tailored for specific livestock species and production systems. High-protein soybean meal serves as a crucial component in poultry and swine diets, while lower-protein versions work well for ruminant animals. The development of specialty soy products represents one of the industry's most innovative frontiers, where traditional processing meets modern food technology. Soy protein isolates, containing over 90% protein, serve as functional ingredients in processed foods, providing structure and nutrition without animal products. Soy lecithin acts as an emulsifier in chocolate and other processed foods, while soy flour enhances the nutritional profile of baked goods. These specialty products command premium prices and demonstrate the versatility of soybeans as a food ingredient. Food-grade soybean processing requires even higher standards of quality control and specialized equipment. Soybeans destined for direct human consumption undergo rigorous cleaning and sorting to remove damaged beans and foreign materials. The processing facilities must meet strict food safety standards, including hazard analysis and critical control points protocols. This attention to quality ensures that soy-based foods like tofu, soy milk, and meat alternatives meet consumer expectations for safety and nutritional value. The international trade in soybeans represents one of the world's largest agricultural commodity movements, with over 150 million tons traded annually. Major exporting countries like the United States, Brazil, and Argentina ship soybeans to processing facilities and livestock operations worldwide. This global trade requires sophisticated logistics networks, including specialized grain handling facilities, ocean-going vessels, and port infrastructure. The efficiency of this trade network allows soybeans produced in the American Midwest to reach consumers in Asia within weeks of harvest. Quality standards and certification programs ensure that soybeans meet international requirements for food safety, environmental sustainability, and social responsibility. Organizations like the Roundtable on Responsible Soy have developed comprehensive standards covering everything from soil conservation to worker safety. These certification programs provide assurance to consumers and food manufacturers that their soybean products meet high standards for quality and sustainability. The environmental benefits of soybean production extend beyond nitrogen fixation to include soil conservation and carbon sequestration. Soybeans in rotation with corn or other crops help break pest cycles and improve soil health through diverse root systems and residue contributions. Modern soybean production practices emphasize conservation tillage and cover cropping, reducing soil erosion and improving water quality. These sustainable practices demonstrate how profitable agriculture can also provide environmental benefits. The future of soybean production continues to evolve through ongoing research and technological innovation. Scientists are developing new varieties with enhanced protein quality, improved disease resistance, and better environmental stress tolerance. Precision agriculture techniques continue to advance, with artificial intelligence and machine learning helping farmers optimize every aspect of production. These innovations promise to increase yields while reducing environmental impact, ensuring that soybeans remain a cornerstone of global agriculture. The remarkable journey of soybeans from ancient Asian crop to global protein powerhouse illustrates agriculture's capacity for transformation and innovation. Through careful breeding, sophisticated processing, and efficient distribution systems, soybeans have become one of the world's most valuable agricultural commodities. This success story demonstrates how traditional farming wisdom combined with modern technology can create solutions to global challenges, providing protein and nutrition to billions of people while supporting rural economies worldwide. The agricultural innovations that have transformed soybean production from precision planting to sophisticated processing represent the same spirit of innovation that drives all modern agriculture. These advances in efficiency, quality, and sustainability continue to reshape how we produce food, creating opportunities for farmers and benefits for consumers worldwide. As we continue exploring agriculture's remarkable achievements, we'll discover how these same principles of innovation and efficiency apply to other essential agricultural systems that support our daily lives. The agricultural innovations that have transformed crops like soybeans into global commodities depend on a partnership so fundamental that without it, our entire food system would collapse within a matter of years. We're talking about one of nature's most industrious creatures, the honeybee, and the sophisticated agricultural systems that manage billions of these tiny workers to pollinate our crops and produce liquid gold in the form of honey. Modern beekeeping represents perhaps the most remarkable example of humans working in harmony with nature, where ancient instincts meet cutting-edge agricultural technology to create something absolutely extraordinary. Consider this staggering fact. A single commercial beehive can house up to 80,000 individual bees, and large-scale beekeeping operations manage tens of thousands of these hives simultaneously. That means a major commercial beekeeper might oversee the activities of over 2 billion bees, more individual workers than the entire human population of most countries. These billions of bees don't just produce honey. They perform the essential service of pollinating crops worth over $200 billion annually worldwide. Without their tireless work, approximately 1/3 of everything we eat would simply vanish from our plates. The modern beekeeping industry generates over $8 billion annually through honey production alone. But this figure barely scratches the surface of bees' true economic impact. The pollination services provided by managed bee colonies are worth an estimated $15 billion annually in the United States alone, making bees some of agriculture's most valuable workers. A single bee colony can pollinate millions of flowers during peak season, with individual bees capable of visiting 2,000 to 5,000 flowers per day. This incredible work ethic makes bees the backbone of modern agriculture, supporting everything from almond orchards in California to apple groves in Washington state. What makes modern beekeeping truly fascinating is how it combines ancient wisdom with space-age technology. Beekeepers today use everything from satellite tracking to monitor hive locations to sophisticated sensors that provide real-time data on hive temperature, humidity, and bee activity levels. Yet the fundamental relationship between beekeeper and bee remains rooted in principles discovered thousands of years ago. This blend of tradition and innovation has created an industry that's both deeply connected to natural processes and thoroughly modern in its approach to efficiency and productivity. The global beekeeping industry spans every continent except Antarctica, with operations ranging from small family apiaries managing a few dozen hives to massive commercial operations that transport thousands of hives across continents following bloom cycles. China leads world honey production with over 450,000 tons annually, followed by Turkey, Iran, and the United States. However, the most sophisticated beekeeping operations often exist in countries like New Zealand, where innovative management techniques and pristine environments produce some of the world's highest quality honey products. Modern commercial beekeeping has evolved into a highly mobile industry, where massive semi-trucks transport thousands of hives across vast distances to follow flowering cycles and provide pollination services. During California's almond bloom, over 2 million hives from across North America converge on the Central Valley, creating one of the world's largest temporary agricultural gatherings. These migratory operations require sophisticated logistics coordination, with beekeepers planning routes and timing moves to maximize both honey production and pollination efficiency. The economic significance of beekeeping extends far beyond honey sales into the complex world of pollination services. Commercial beekeepers rent their hives to farmers during bloom periods, with rates varying from $150 to $250 per hive depending on the crop and region. This pollination rental business has become so valuable that many beekeepers derive more income from pollination services than from honey production. The timing of these services requires precise coordination with agricultural cycles, as bees must arrive just as flowers begin opening to maximize pollination effectiveness. Understanding the biology and behavior of honeybees forms the foundation of all successful beekeeping operations. A typical honeybee colony operates as a superorganism, with each individual bee performing specialized roles that contribute to the colony's overall success. The queen bee, the colony's only reproductive female, can lay up to 2,000 eggs per day during peak season. Worker bees, all female, perform various tasks including nursing young bees, building comb, foraging for nectar and pollen, and defending the hive. Drone bees, the males, exist solely to mate with queens from other colonies, representing nature's ultimate specialists. The annual cycle of a bee colony follows predictable patterns that modern beekeepers have learned to manage and optimize. Spring represents the build-up phase, when colonies emerge from winter dormancy and begin rapidly expanding their populations. Summer brings peak activity, with maximum foraging and honey production occurring during this period. Fall represents the harvest season for beekeepers, when excess honey is removed and colonies begin preparing for winter dormancy. Winter requires careful management to ensure colonies survive until spring buildup begins again. Modern hive design represents centuries of evolution in beekeeping technology, culminating in the standardized Langstroth hive that dominates commercial operations worldwide. These rectangular hives consist of stacked boxes containing removable frames, allowing beekeepers to inspect colonies and harvest honey without destroying the comb structure. The precision engineering of modern hives ensures optimal bee space, the critical 3/8-inch gap that allows bees to move freely while preventing them from building unwanted comb. This standardization has revolutionized commercial beekeeping by enabling rapid hive manipulation and efficient honey extraction. The establishment of new bee colonies begins with understanding the complex social dynamics that govern colony reproduction. When colonies become overcrowded, they initiate the swarming process, where the old queen leaves with approximately half the worker bees to establish a new colony elsewhere. Modern beekeepers have learned to manage this natural process, either preventing swarming through colony manipulation or capturing swarms to establish new hives. Commercial queen rearing operations produce thousands of queens annually, allowing beekeepers to establish new colonies or replace failing queens with genetically superior stock. Queen rearing represents one of beekeeping's most sophisticated arts, combining deep understanding of bee biology with precise timing and technique. Commercial queen producers maintain specially managed colonies that produce large numbers of queen cells, each containing a developing queen bee. These queen cells are carefully timed to emerge when mating conditions are optimal, ensuring that new queens can successfully mate and begin laying eggs. The process requires maintaining exact temperatures, providing optimal nutrition, and timing operations to coincide with drone availability for mating. The development of bee colonies from small starter units to full-strength production hives requires careful management of resources and timing. New colonies typically begin with a few thousand bees and a young queen, gradually building population through successful brood rearing. Beekeepers must provide adequate space for colony expansion, monitor for diseases and pests, and ensure sufficient food resources during build-up periods. This growth process can take 6 to 8 weeks under optimal conditions, transforming a small starter colony into a full-strength hive capable of significant honey production. Nutrition management in modern beekeeping involves understanding the complex dietary needs of bee colonies throughout their annual cycle. Bees require carbohydrates from nectar and honey for energy, proteins from pollen for brood development, and water for various physiological processes. During periods when natural food sources are scarce, beekeepers provide supplemental feeding using sugar syrup for carbohydrates and protein supplements for brood development. This nutritional management ensures colonies maintain optimal health and productivity throughout the season. Disease and pest management represents one of modern beekeeping's greatest challenges, requiring integrated approaches that combine prevention, monitoring, and treatment. Varroa mites, microscopic parasites that weaken bees and transmit viruses, represent the most serious threat to bee colonies worldwide. Modern beekeepers employ various treatment methods, including organic acids, essential oils, and integrated pest management techniques that minimize chemical residues while maintaining colony health. Regular monitoring and early intervention are crucial for preventing small problems from becoming colony-threatening disasters. The foraging behavior of honeybees demonstrates nature's most efficient resource collection system, with individual bees capable of communicating the location of distant food sources through sophisticated dance languages. Scout bees locate flowering plants and return to the hive to recruit foragers through precise waggle dances that indicate both direction and distance to food sources. This remarkable communication system allows colonies to rapidly mobilize thousands of workers to exploit newly discovered resources, maximizing collection efficiency while minimizing energy expenditure. Modern beekeepers have learned to manage foraging resources by strategically placing hives near abundant nectar sources and timing management activities to coincide with peak flowering periods. Understanding local bloom schedules allows beekeepers to position colonies for maximum honey production while ensuring adequate pollination services for agricultural crops. This resource management requires detailed knowledge of local flora, weather patterns, and agricultural practices, making successful beekeeping a sophisticated blend of science and art. The honey production process begins in the field, where foraging bees collect nectar from flowers and begin the transformation process immediately. Bees add enzymes to nectar while it's still in their honey stomachs, beginning the conversion of complex sugars into the simple sugars that characterize mature honey. Back in the hive, house bees continue this process, repeatedly ingesting and regurgitating the nectar while adding additional enzymes and reducing moisture content through evaporation. Comb construction represents one of nature's most remarkable engineering achievements, with bees creating perfectly hexagonal wax cells that provide maximum storage capacity with minimum material usage. Worker bees secrete wax scales from specialized glands, then chew this wax to proper consistency before molding it into comb structures. The hexagonal shape of honeycomb cells represents an optimal solution to the mathematical problem of maximizing storage space while minimizing construction materials, the solution that continues to inspire modern engineers and architects. The ripening process of honey requires precise moisture control, with bees fanning their wings to evaporate excess water until honey reaches approximately 17 to 18% moisture content. This low moisture content prevents fermentation and gives honey its remarkable shelf life. Bees cap completed honey cells with a thin layer of wax, creating a sealed storage system that can preserve honey for years. This natural preservation process has made honey one of humanity's most valued food products, with archaeologists regularly discovering edible honey in ancient tombs. Modern honey extraction represents a sophisticated balance between efficiency and quality preservation, using specialized equipment that removes honey while leaving comb structures intact for reuse. The extraction process begins with uncapping, where thin wax caps are removed from honey cells using heated knives or specialized uncapping equipment. The uncapped frames then go into centrifugal extractors that use spinning motion to force honey out of cells while leaving comb undamaged. This process allows beekeepers to harvest honey multiple times per season while maintaining productive comb for future use. Quality control in honey production involves multiple testing procedures to ensure purity, authenticity, and safety. Modern honey testing includes moisture content analysis, sugar profile verification, and contamination screening for pesticides and antibiotics. Advanced testing techniques like nuclear magnetic resonance can detect honey adulteration and verify floral sources, ensuring that products meet strict quality standards. These quality assurance processes are crucial for maintaining consumer confidence and accessing premium markets. The grading and classification of honey involves evaluating multiple characteristics including color, flavor, moisture content, and floral source. Light-colored honeys like clover and alfalfa typically command higher prices for table use, while darker honeys like buckwheat and wildflower often serve industrial applications. Specialty honeys from single floral sources like orange blossom or tupelo can command premium prices in gourmet markets. This product differentiation allows beekeepers to maximize returns by targeting specific market segments. Processing and packaging of honey requires maintaining product integrity while meeting diverse market requirements. Some honey is sold raw and unprocessed, retaining all natural enzymes and pollen content. Other honey undergoes pasteurization and filtration to create products with extended shelf life and consistent appearance. Specialty processing techniques can create whipped honey, infused honeys, and other value-added products that command premium prices in retail markets. The global honey trade represents a complex network of producers, processors, and distributors moving over 2 million tons of honey annually. Major honey exporting countries include China, New Zealand, Argentina, and Ukraine, each offering different honey types and quality levels. This international trade requires sophisticated logistics systems and quality certification processes to ensure products meet importing country requirements. The honey trade also faces challenges from adulteration and mislabeling, requiring advanced testing and verification systems. Pollination services represent the beekeeping industry's most valuable contribution to agriculture, with managed bee colonies providing essential pollination for crops worth billions of dollars annually. Almonds, apples, blueberries, and dozens of other crops depend on bee pollination for successful fruit and seed production. Commercial beekeepers coordinate with growers to ensure adequate bee populations arrive during optimal bloom periods, requiring precise timing and careful hive management to maximize pollination effectiveness. The logistics of commercial pollination involve massive migrations of bee colonies following bloom cycles across continents. Beekeepers load thousands of hives onto specialized trucks for transport to pollination sites, often traveling hundreds of miles to reach contracts. This migratory beekeeping requires sophisticated planning to coordinate with agricultural schedules while maintaining colony health during transport and placement. The scale of these operations during major bloom periods like California almonds creates temporary cities of beehives that rival small towns in population. Technological innovations in modern beekeeping include electronic monitoring systems that provide real-time data on hive conditions, GPS tracking for migratory operations, and automated feeding systems that ensure optimal nutrition. These technologies allow beekeepers to manage larger numbers of colonies more efficiently, while maintaining high standards of animal welfare and productivity. Smart hive systems can alert beekeepers to problems like swarming preparation or disease outbreaks, enabling rapid intervention to prevent losses. The environmental benefits of beekeeping extend beyond crop pollination to include support for wild plant communities and biodiversity conservation. Managed bee colonies often spill over their pollination services to wild plants, supporting ecosystem health and plant reproduction. Modern beekeepers increasingly focus on sustainable practices that support both bee health and environmental conservation, including habitat restoration and pesticide-free management practices. Research and development in beekeeping continues to advance through collaboration between beekeepers, agricultural scientists, and technology companies. Current research focuses on developing mite-resistant bee strains, improving nutrition supplements, and creating more efficient hive designs. These innovations promise to enhance colony health and productivity while reducing management costs and environmental impact. The future of beekeeping faces both challenges and opportunities as global demand for pollination services continues to grow. Climate change, habitat loss, and evolving pest pressures require adaptive management strategies and continued innovation. However, increasing recognition of bees' crucial role in agriculture and growing consumer demand for honey products create opportunities for industry growth and development. The remarkable world of modern beekeeping demonstrates how human ingenuity can work in harmony with natural systems to create mutually beneficial relationships. From the sophisticated social organization of bee colonies to the advanced technologies that monitor hive health, beekeeping represents agriculture at its most collaborative and sustainable. The billions of bees working in managed colonies around the world continue to provide essential services that support our food systems while producing one of nature's most treasured products. The journey through sugar processing, soybean production, and beekeeping reveals the incredible complexity and sophistication of modern agriculture. Each system represents decades of innovation, combining traditional knowledge with cutting-edge technology to feed our world and support rural economies. These agricultural achievements demonstrate humanity's capacity for innovation and collaboration, creating abundance from the fundamental partnership between human knowledge and natural processes. As we've discovered, modern agriculture extends far beyond simple farming into complex systems that transform raw materials into essential products while supporting millions of livelihoods worldwide. The precision, scale, and efficiency of these operations represent some of humanity's greatest achievements, creating the abundance that supports our modern world. Whether it's the crystalline perfection of processed sugar, the protein-rich versatility of soybeans, or the golden sweetness of honey, these agricultural systems continue to evolve and improve, promising even greater achievements in the years ahead. If you found this deep dive into modern agriculture as fascinating as we have, make sure to subscribe to our channel and hit that notification bell so you don't miss our upcoming explorations of the remarkable world of food production. From the fields where it all begins to the sophisticated processing facilities that create the products we use every day, agriculture continues to amaze with its combination of tradition, innovation, and sheer scale. Join us as we continue uncovering the incredible stories behind the food that powers our world.